Welcome to the design presentation conducted by Group 3 of the Integrated Design module. Emil Sebastian, Jonathan Ridgway, Matthew Pearson, Jack Schilling and Ben Polson. The task at hand was to design an energy system that could harbour potential sea energy.
The EMSWIS project had to design a device that will generate energy from the sea, while taking all environmental concerns into consideration. The device will need to be able to operate efficiently and continuously, and require as little maintenance and workers as possible.
Within the energy of the sea, there are 3 accessible energy sources. These are tides, waves, and ocean currents. Tidal energy uses the increase and decrease in ocean tides. It does this by containing a large amount of water, then releasing the water through a turbine once the tide has fallen. In wave energy, there are many devices that are based on the oscillating movement of the sea to harness this energy. Some devices use this to move a hydraulic pump, which in turn powers a turbine. Current energy uses a continuous flow of water to turn a turbine.
An attenuator is a device that consists of a semi-submerged structure that has multiple segments connected by hinge joints. As waves pass, the segments move with the wave, displacing hydraulic pressurized oil, which is pumped into a hydraulic motor that powers an electric generator. Point absorbers are devices that are relatively small and are either bottom-mounted or a floating structure. The vertical motion of the buoy is utilized to compress gas or liquid in a container, converting the pressure into rotational movement of a power generator. An oyster device is an almost completely submerged device which pitches back and forwards in the nearshore waves. The movement of the flap drives 2 hydraulic pistons which push high-pressure water onshore through underwater pipes to drive a conventional hydroelectric turbine. An oscillating water column is a device where waves act like pistons, forcing air through a Wells turbine and then pulling it back in. The use of this turbine allows the generator to spin in the same direction regardless of the direction of the air. The bulge wave device is a rubber tube filled with water that is moored to the seabed. Water enters through one end, creating a bulge of pressure. The wave carries it down the device, where it builds up energy that can be transferred in a small turbine.
A decision matrix was used to help decide which wave energy device would be best suited. Location, potential for creativity, environment, aesthetics, and ultimately our preference were the factors taken into account. After totaling it up, the decision was to take on the energy device with the highest marks. This was the oscillating water column.
Oscillating water column is a type of wave device which is used to generate electricity. It works in the basis of air pressure. The oscillating water column is often placed over breakwater so that the water can enter into the column with its full potential. The oscillating water column device consists of a column, turbine, and a generator. The generator is placed at the top of the column. As the water enters the column, it builds up the air pressure and tends to push the air outwards. When the air passes through the turbine, it drives the turbine and generates electricity. The column also retracts the fresh air from outside because when the water flows off the column as a part of wavefall, the column absorbs the air from the outside, like a vacuum, which then further drives the turbine. This continuous process rotates the turbine continuously, and as a result, the generator generates electricity without any interruptions.
The Wells turbine is a low-pressure air turbine that rotates continuously in the same direction despite the direction of airflow. It does this by the use of symmetrical airfoils on the blades of the turbine. These airfoils have to be carefully situated so that the plane of symmetry is in the plane of rotation and perpendicular to the airflow. They were purposefully designed for an oscillating water column where a rise fall in water creates an oscillating airflow.
Similar devices are being used in several countries throughout the world, including Australia, Japan, India, Portugal, and Scotland. Northwest areas of the USA, such as Oregon and Alaska, have oscillating water columns installed. The east coast of New England is also an appropriate location. Waves with high potential energy approaches the coast of Oregon, Alaska, and New England.
The designing and building of this device will create jobs and work for local businesses, as well as providing energy for the local area. With Plymouth Breakwater already being a stable structure, only minor changes would be required to make it suitable for an oscillating water column. Also, with it being away from the mainland, it will be an ideal place as it is out of sight and sound.
Our design features a 30-metre long, 5-metre wide and 3-metre tall tunnel. This is attached to the turbine housing which sits on top of the flat breakwater section. There are 4 support columns, 2 standing side by side 10 metres from each end. The length of the tunnel is designed to be able to receive an intake of water at various tidal points. The turbine housing features 2 vents on either side to allow the air to flow in and out of the system, preventing choking. These vents have shrouds to help stop water getting into the housing. Inside the turbine housing is the turbine and generator, and attached to the turbine is a Wells turbine with a diameter of 1.2 metres, which is almost flush with the hole in the housing, encouraging air to power the fan rather than escape around the sides. The tunnel has 2 ridges on its roof, which act to both prevent water from flowing up it and to also provide extra foundation to the support columns.
These flyboys will show you the 3D model we have created in SolidWorks. The design features a rounded entrance to promote water flow, as well as support columns to prevent the tunnel from collapsing when water flows on top of it. Our device will be situated at some point along the long, sea-facing strait. As the wave chart shows, Plymouth will experience waves between 4 and 8 feet tall.
Plymouth Breakwater is continuously being maintained, which involves money being spent, so an investment into a wave energy generator to be built upon it could have their green energy being used on the breakwater to power the lighthouse and other lights, or sold to help fund the maintenance. Plymouth in general is a large city that requires a lot of energy, both on land and at sea. Having an energy source built in Plymouth for the benefit of Plymouth would contribute to the massive energy demands. Also, environmental parties will have to be informed on the design to ensure the device complies with rules and regulations and doesn't upset or cause disturbance in such areas.
The power output from an oscillating water column is directly linked with the local wave climate. The climate with high waves will have the most powerful output from the device, whereas the low power output is when the wave climate is poor, as the waves will have low potential energy. In Australia, the government has installed an oscillating water column called Green Wave Ocean Links. A single green wave device produces about 1 megawatt or more during a period of strong waves.
Here are some of the advantages of the oscillating water column. There are no fuels required to power it. The energy produced will be more predictable than, say, wind. Turbines aren't in contact with corrosive seawater, so they will last longer, and it can be built near the land for easier access. The disadvantages of this project are: initial building costs are high, the machine would need to withstand extreme weather, so higher building tolerances and safety factors would need to be considered, and the device would be placed in an area with a high density of marine life. Some of this life would be displaced to other areas of the breakwater.
There are many aspects of the design process that need to be considered if the design is to stay within current UK legislation, as shown by this diagram. The power generator from the oscillating water column could be used to power the lighthouse situated on the west end of the breakwater. The power cables would be buried in the breakwater to avoid potential interferences and damage. They would be waterproofed and pressure resistant.
If successful, multiple columns can be placed along the Plymouth breakwater, as well as others across the UK. Research for the report will consist of information regarding legislations, building regulations, materials to be used, and the predictability of Plymouth's weather.
A Gantt chart was created at the beginning of the project to plan out our goals and monitor our progress. It is an efficient method of keeping track of the project time limit, which we use to our full advantage.
The aims that were set for this presentation at the beginning of the project are believed to have been successfully met. A wave energy device has been designed that would effectively harness electricity from the sea and in a relative location. The next stage of the project is to create a physical model that can demonstrate the basic actions of the oscillating wave column and write a detailed report.
This Gantt chart was created to plan out our objectives for next term and show our goals for the next stage of the project.
Here is a summary of the theory we will apply to the report, as well as the final model.